Given an array, can you turn it into a tree? And this tree must keep the array's original order, yet behave like a heap. For now, assume distinct values, so every parent is smaller than its children. That is exactly what a Cartesian tree does. A Cartesian tree is built from an array. We use this one for the demo. 3, 2, 5, 1, 4. The minimum of the whole array, 1, becomes the root. It splits the array into a left and a right part, and each part recursively takes its own minimum as a subtree root. In real implementations, duplicate values need a fixed tie-break rule, such as using the index when values are equal. That keeps the tree unique. Remarkably, an in-order traversal of this tree gives back the original array exactly. 3, 2, 5, 1, 4. The order is fully preserved. First property. A node's in-order position matches its index in the array. So with respect to indices, a Cartesian tree is a binary search tree. Second property. With distinct values, every parent is smaller than its children. A minute heap on values. A search tree on indices, a heap on values. That duality is what defines a Cartesian tree. Naive recursive minimum finding costs, big O of n log n, or even big O of n squared. A monotonic stack brings it down to linear big O of n. The stack always holds the nodes on the current right spine of the tree, increasing from bottom to top. Process the first element, 3. The stack is empty, so just push it. Stack is now 3. Process 2. The top of the stack, 3, is larger, so pop it. The popped 3 becomes 2's left child. Then push 2, and the stack becomes 2. Process 5. The top, 2, is smaller, so nothing is popped. So 5 attaches as 2's right child and is pushed. The stack becomes 2, 5. Process 1. It is smaller than everything on the stack, so pop 5 then 2. The last popped node, 2, together with its whole subtree, becomes 1's left child. Push 1, and the stack becomes 1. Finally, process 4. The top, 1, is smaller, so 4 becomes 1's right child. We scan the array only once, and each element is pushed and popped at most once, so the whole construction is big O of n. The classic application is range minimum query. The minimum over any interval I, j is exactly the lowest common ancestor of nodes I and j, so RMQ reduces to an LCA problem. From another angle, a treap is a Cartesian tree. Keys satisfy binary search tree order, while random priorities satisfy heap order, keeping it balanced in expectation. It is intrinsically tied to the monotonic stack, so classic problems like the largest rectangle in a histogram map naturally onto the Cartesian tree view. And all of this rests on being buildable in big O of n linear time, which is the foundation of its practical value. A Cartesian tree fuses array order and heap order into one tree. In order gives the array, values form a minute heap, and duplicates need a tie-break rule. It can be built in big O of n time with a single monotonic stack. That is why it underlies range minimum queries, treaps, and a whole family of monotonic stack problems.